Thanks to the organizers for putting together this lovely meeting and for this opportunity to speak. But I understand I am the person sitting or standing between you and the coffee. Sorry, sorry about that. So this is a talk about the Unruh effect, this prediction in relativistic quantum field theory saying that the acceleration of an observer affects what that observer sees. Okay? I'll be talking specifically about the circular motion version of the Unruh effect. And the reason is that there are ongoing and in development experimental proposals to observe this effect in an analog space-time setting in the laboratory. The sort of driving experimentalist force here is Silke Weinfurtner at Nottingham, and this work is being done in her gravity laboratory there. The two main references for what I'll say are these two papers, but I'll mention some more recent work and some work in development as we go along. So this is a talk at the interface of theory and experiment. I should come clean and say I am a theorist, so I will be on the theory side, but I will make some experimental comments when at appropriate places. So the plan is, I'll first recall a few things about the Unruh effect, this prediction that acceleration affects observation, both in the relativistic space-time setting and in the analog space-time setting. Then I'll talk about the devices, the theoretical devices that we usually use to describe this effect, and this is sense of temperature that I want to talk about. Then circular motion is what we hope to observe, and I'll talk a little bit about how the circular motion is different in 3+1 and 2+1 dimensions, 2+1 being the case where we hope to be able to do the experiment. And then I'll tell about the theory results. So the effect, I will claim, is there and is there waiting to be observed. And in the summary, I'll mention some of the things that it would take to actually go and observe it. Okay, and I understand that the format is such that I should invite you to store questions and then ask in memory and then ask the questions at the end of the talk. Okay, so background, Unruh effect. This prediction that observer's acceleration affects what that observer sees in relativistic quantum field theory. It's a basic prediction, some 45 years old by now. And the showcase example is uniform linear acceleration in Minkowski space in Minkowski vacuum. The prediction is that observer sees Minkowski vacuum as if it was a thermal state in a temperature proportional to the acceleration. There are some technical qualifications to this, but that's the basic prediction. And this prediction is an observable prediction. It's not just some descriptions of some equations you write on a piece of paper. And so my favorite way to think about it is that you are in your spaceship, you keep speeding, and on your shelf there you have a jar of different kinds of atoms, and you have antimony, arsenic, aluminum, selenium, and so on. And once in a while you look in those jars and you see what fraction of the atoms are in their ground state and what fraction are in their excited state. And you'll find it differs from jar to jar because there are different energy gaps. And the prediction is the populations up and the populations down, they follow this law, the detailed balance law. There is the gap between the two states, and there's the temperature, is a single parameter that describes this case. So this is a real effect. It's so real that you can cook your steak with it. However, to date, no states have been cooked with this effect because you put in the numbers, right? So I was using geometric units. You put in the numbers, there are constants of nature there, and a calculation says 1 Kelvin would require 10 to 20 meters per second squared. So in this relativistic space-time setting, a hard thing to observe. And so there are proposals, there are decades of proposals to make this effect more observable. In particular, there are proposals to go to circular motion. These go in particular down to Bell and Linus, who considered acceleration, particle accelerator storage rings. So one selling point of circular motion is that you can keep your accelerating system in a finite sized lab for a long time, in principle, an arbitrarily long time. You can't do this in linear acceleration. So this is certainly a selling point if you're writing a grant proposal. You can keep the thing in your lab. Okay, so there are theory works. There are these theoretical proposals. What I want to concentrate on is this recent proposal in these papers that I mentioned, to see this on a desktop size system, perhaps Bose-Einstein condensate, perhaps superfluid helium. So yes, so why now? There are these experimental proposals. So the desktop experiment in circular acceleration, there are two major selling points. One is this finite lab thing, finite size lab thing that I already mentioned. The second thing is that in a laboratory system, in a condensed matter system, you may be able to simulate a relativistic wave equation, maybe Klein-Gordon equation, some systems may be the Dirac equation and so on, but you can't easily simulate time dilation. And the time dilation is an essential part of the conventional relativistic spacetime version of the Unruh effect. So how do you deal with time dilation? The circular motion has the selling point that it is a stationary system. Okay, there's acceleration, but it's still stationary in your laboratory. And that means you can put in the relativistic gamma factors in the system at the time of the data analysis. You don't need to tell your experimenter to go and put a relativistic time gamma factor in the solid state system. You can do it at the time of the data analysis. So those are the two selling points. I've here a graph lifted from one of these experimental proposal papers. There's a Bose-Einstein condensate, and then there's a proposal to put a laser beam there to collect the fluctuations and so on. Let me not go into that side of the things. So today, I want to convince you that there is an effect there that is waiting to be seen. And the tool that I'll use to consider this effect is, well, I'll call it a quantum dot. You've seen it in a number of previous talks. It's really an Unruh detector, okay? But it's a quantum dot. I'll use it as a theory tool to say what the effect there is in the solid state system waiting to be absorbed. And I'll tell a little bit of, so I want to in particular ask what's the notion of temperature you have over there. And experiment might take place in 2+1, so a little bit about this. What not in this talk is how the actual experiment is going to work. This is about the phenomenon there that's waiting to be observed. Right. So the quantum dot. I've got three overheads about the quantum dot. I'll say a few words about each of those overheads. So this is the Unruh DeWitt detector about which we've heard on many talks. So basically for me, it's an atom with internal structure almost completely forgotten. It's a spatially point-like system, and you make it go through a space-time, in this case on a circular orbit. It's a spatially point-like local quantum system. You might expect that if you have something that's spatially point-like, your theory is going to go singular at some point, and it is, but in the order of perturbation theory in which I'll be working, it won't matter. So this is still perfectly okay. So, right. So, so there's some terminology you need to do to set it up. It's really just a two-state system. The key point is there is a linear interaction over there. It's like a poor man's model of how atomic orbitals couple to the quantum electromagnetic field. So that's the input side of the theory. Then there's the calculation side of the theory, and it takes one overhead. You do time or time-dependent perturbation theory. You ask what is the probability for your quantum dot to change its quantum state, maybe upwards, maybe downwards, but you calculate the probability of the change. And yeah, you calculate it, and you find that this probability, it knows about the quantum field only through this two-point function. The one reason why we are interested in two-point functions in quantum field theory. Okay, so the two-point function tells us what's going to happen. So that's the calculation side of the theory. Then there's the application side of the theory, my third theory overhead. And that says, well, we are here in a stationary situation with a circular motion. Okay, so time dependence can be simplified, and you can even forget about the switch on and switch off effects. You go to transition rates rather than probabilities. And then this is the fit you do. This is, remember the detailed balance formula we looked at early on. Your theory tells us what these excitation and de-excitation probabilities is. You fit them to this exponential laws. And that gives you a prediction for the temperature-like quantity that you would see. In linear acceleration, it's a genuine temperature independent of anything. There's the Unruh temperature. For the other uniform motions, and in particular for the circular motion, well, it's a sort of energy-dependent temperature. It's nevertheless useful as a quantifier of what the phenomenon there is that we are looking for. Okay, so that was the theory. Now, in practice, so we want to put it on a circular motion, right? Effective spacetime metric Minkowski, uniform circular trajectory. We know how to write those things down. There are some gamma factors there, but we know how to deal with that. And I'll specify to the massless scalar field, and that is what we hope to see in a Bose-Einstein condensate. Possibly also superfluid helium. And then the Whiteman function, the thing that carries the quantum information, there it is. So there's the space-time straight line distance along the trajectory. At this point, you see that there is some difference depending on what space-time dimension is. I'll come to that at the very end. Okay. And now we've got all the theory and practice part together. Now you just plug this in the formulas, and you want to ask how good, so is there a phenomenon to be seen? How is it related to the linear acceleration phenomenon that we know and love? In the theory paper, we do lots of asymptotics and so on. For the purposes of today, I'll skip the technical merits and I'll go directly for the artistic impression. I'll show two overheads of plots. So, oh, sorry. Okay. So there's one small bit of theory. I'll come to that at the very end. So let's do first the relativistic space-time. Imagine that you're in a spaceship and you're actually be able to do that. So I'd like to ask how similar, how different is the circular motion temperature to the linear motion temperature? I'm plotting here on the vertical axis the ratio of the circular motion and the linear motion temperatures. Okay, both in 3 + 1, 2 + 1 dimensions in terms of the relevant parameters there. Well, it's not a constant. I mean, if it was constant, you'd expect a plane like that, and it's not a constant. So there's something different from the circular acceleration. But if you look at the actual scales, it's not too different. It's order unity, and you can back that up by doing asymptotics along the plotted regimes. There's a little bit of difference there in 2 + 1 dimensions. It's a peculiarity of 2 + 1 dimension. But in relativistic spacetime, it's basically the same thing. There is a phenomenon to be seen. Analog spacetime, I'll flip the overhead. Similar things plotted in the analog spacetime with the gamma factors put in the right places. See if you can spot the difference. So relativistic spacetime, analog spacetime. Relativistic. Analog. Okay, there's a little bit of a difference, but basically it's the same story. Okay, there's there's some fine print, but I'll suppress the fine print. It's basically the same story. There is a phenomenon to be seen, and there is a phenomenon to be seen in these analog space-time systems. And I understand that I'm essentially out of time here, so I've been trying to convince you that circular motion in an analog space-time system, desktop experiment, is a good place to look for the circular motion. Unruh effect and the Unruh temperature, it is a useful way to describe this. And the theory says, brought by this quantum dot, yeah, it's basically the same thing. In 2 + 1, in Bose-Einstein condensate, you need to be careful with the parameter space a little bit, but basically it's the same story. Thank you. Okay, so this was the simple setting. In a real experiment, you don't have a vacuum. You have finite temperature. There's a finite size system. Then you need to worry about back action at some point. And we have posters about this topic here. We also have a talk after the break about the back action effect. And there's some names involved here. So that's the theory. And what we'd really like to do is the experiment, okay? And some things are already in experimental construction in Nottingham, okay? But you can't go to Amazon and order a quantum dot. Okay? What you can order is a laser. You can shine that laser through the system, and then you can start collecting those fluctuations through those from that laser. How similar do we think that is to the quantum dot over here? You may remember I showed those two formulas about the Whiteman functions. In 2 + 1, there was a square root. In 2 + 1 for time-like distances, in time-like separations in the vacuum, the Whiteman function is purely imaginary. You can't measure a purely imaginary number, okay? Every experiment you do will measure a real number for you. Now, the imaginary thing, it's not a problem for the quantum dot. I mean, Hermitian operators have real eigenvalues, even if there's something imaginary off the diagonal, provided there's something negative imaginary on the other side. So the quantum dot is a Hermitian operator in the right sense and knows how to deal with this. How the laser beam might know about this? There's something to be done here, and this is why I've been having such a lousy time with quantum optics textbooks over the last few years. There's something there to be understood. We think we are on the right way. Hopefully, I'll be able to tell about that at some future meeting. Thanks very much for your attention.
We're on time, so yes, just one question. So let's go in. Yeah.
Hello, Jorma. Thank you for the talk. My question is that your temperature for the circular case depends on the gap of the detector. Now, from thermodynamics, my way of understanding a temperature always is, well, the temperature cannot depend on the thermometer. If I plug in a thermometer made of mercury or one made of alcohol, it should give me the same number. Your temperature depends on the detector. So to what extent is okay to call it thermal? If we go with the definition of, I understand though, it's beautiful, it's not a criticism, but the calling it thermal or the analogy with the Unruh effect, you see, because then we go to the other extreme, which is, any detector that is non-inertial I can define an effective temperature through the detailed balance condition. Let's call it EDR temperature, excitation, de-excitation ratio temperature. So would you call Unruh effect to any motion, no matter what? If a detector gets excited through any motion, would you call it Unruh effect? And also then the dynamical Casimir effect, is all those different names for the same thing for you? For me personally, I think for the thermality part, not depending on the thermometer or in the gap in this case. Anyway, yeah.
There are different authors, different workers who make this distinction in different ways. For example, in the Scolapedia article by Fulling and Matzes, they make a strict distinction between a genuine thermal bath and then the temperature-like thing you see in the other uniformly accelerated motions. This is to some extent a point of view, okay, let me make an argument here. If we say the temperature of this desk is 20 degrees centigrade, we haven't measured it using gamma rays, have we? We don't care what the gamma rays do when they are here. They go through here. We don't care about the radio waves when they go through this desk. We look at a certain band of excitations when we say that the temperature here is 20 degrees. It's in the same sense that this gap-dependent notion of temperature is introduced here. It is the effective temperature seen by the detector in a certain energy gap. In different energy bands, things might look like different. In fact, quite different. In fact, we saw in the plots that in the 2+1 case, there are some gap regimes where things do look quite different.
How do you different between linear and circular? Or any other motion?
Well, I refer to Leo Parry's poster out there. He will be able to tell more about that.
Thank you.
Okay, let's say German again.